All right, let's get started here on the second part of this many cavities session, and we have the crazy man himself, Jon.
Yeah. Okay. It's great to be here. Normally, I guess I would thank the organizers, but that seems a little weird. So I think what's maybe more appropriate is to thank all of you for coming and making this so fun and lively. I'm really having a good time. I hope you are too. So what I'm going to tell you about today at a granular level is two projects that are ongoing in my group and in my collaboration with Dave Schuster's group, making arrays of optical cavities and making megahertz update rate spatial light modulators. This may seem like a little bit of a weird topic for a cavity workshop, but I think the thing that's sort of interesting is that it comes from a unified perspective on optics. And so what I wanted to do was sort of riff on what Dan said. I actually made all of these slides after Dan made this comment about non-quadratic optics. So this whole talk was made by AI in the last 5 minutes. No, that's not true. But I do think it's important to say that quadratic cavities are really special objects. And so before we even hop into what it is that we've been doing, I want to say what I mean by that. If I have a pair of mirrors like this cavity has either one axis or an infinite number of axes. And what do I mean by an axis? An axis is a ray trajectory that comes back to itself under a round trip, okay? So what do I mean that this cavity has one axis? There is one ray that comes back to itself under a round trip. What do I mean by an infinite number of axes? If I go to a confocal point, a half confocal point, any of these points, then under some number of round trips, the rays come back to themselves, but it's not a discrete ray that comes back to itself. It is a continuously infinite set of rays that come back to themselves, okay? And this is a consequence of the fact that your cavity is made of quadratic objects. So if I make a mirror which is not a quadratically shaped object, I can have a situation where this central ray comes back to itself, and that weird ray out there comes back to itself under a round trip, and nothing in between actually does. So this is sort of the philosophy that we've been working towards, move away from these quadratic paraxial optical elements and see what new capabilities come from that. So the smallest move you can make is to have non-paraxial optical elements, non-quadratic elements, but all of your optics is paraxial. How can those two things be the case? Well, the idea is that I can still find cavity axes, okay, by tracing rays that come back to themselves, but when I perturb around those rays, I only am looking at small changes, small wavefront distortions compared to the plane wave corresponding to that ray. So what's our recipe? Trace rays through your system, find the closed paths, and then compute local ABCD matrices with respect to those closed paths. So what does this look like? And then we can expand transverse modes around each of those axes. So I'll give you an example. What is the axis of this cavity? Well, sorry? That's an axis. Isn't that also an axis? So this is actually a cavity that has two axes, right? Even if these are quadratic optics. And so I think it's sort of an interesting thing. You can do this with many different systems that you make. You can generate these additional axes. For this one, you would not be at all confused about how to compute the mode structure, right? What you would do is you'd say, like, okay, I'm going to compute an ABCD matrix here. I know how to compute an ABCD matrix here because I'm hitting this off axis, and Sigmund says that I should do some expansion in angles. Actually, Sigmund doesn't tell you to do an expansion in angles. It just tells you what the off-axis ABCD matrix is for the mirror. And then you can compute your ABCD matrix. If you didn't have that, what you would do is try to figure out what the ABCD matrix is, and how would you compute that? Well, what you would do is first displace array slightly with respect to this axis and trace it around. Sorry, I was doing it in this picture. Yeah. So what I would do is displace array slightly with respect to this axis and trace it around the cavity and see, once it goes once around, how displaced it is in position with respect to my input ray, and that's this element, and how much displaced it is in angle, and that's that element. And then I can also displace an angle and trace around and compute the second row of my ABCD matrix. Okay? And so the philosophy of what we're doing at a high level is to say, we're going to put crazy optics into our cavity. We're going to ray trace how they behave, right? And then we can expand modes by generating these ABCD matrices for each ray that comes back to itself, and that'll give us our family of cavities. I think that served its purpose. It's warmed up now, though, if anyone needs it. All right. So what is the cleanest non-paraxial optic you can put into your cavity? It is a microlens array. And so you can see immediately that if you put a microlens array between a pair of mirrors, you get an array of cavities based on this kind of a picture. There are probably other cavities that you could generate in this as well, but that's sort of the fundamental point of this. This is a extraordinarily non-quadratic optic, but we can still tell locally quadratic stories around each of those axes. And the great thing is that everybody sells these things, and it turns out they're drawn as though they're quite thick objects. The height of these lenses is basically limited by microfabrication to a couple of microns. So with rare exceptions, these things are a few microns tall, and their heights are accurate, as we've now seen in our lab, 2 nanometers, right? So they're very, very pristine, precise objects. So that's the background for what I want to tell you about today. The science is sort of built around this idea that light collection is king. From detecting the state of an atom to bell pair distribution, we really care about what fraction of the light an atom emits we're collecting. Our detection time scales inversely with our collection efficiency. Our heating per collected photon scales inversely with that collection efficiency. And our entanglement generation rate scales inverse quadratically with that efficiency. And so if you want to do quantum many-body physics, quantum computing, any of these things, you really care about those numbers. Of course, there's an overall prefactor, which is set by how quickly my atom decays. But of course, cavities can also improve that. So what are our targets going to be? We want to make the collection efficiency fast. We want to make the atoms decay fast. So we want to have cavities. We'd like to do this for thousands of atoms in parallel. And we'd like to avoid stray electric fields. So that means we need some kind of a crazy cavity array geometry, which enables us to keep our atoms centimeters almost from any surface, but also in cavities with micron scale mode waste. So what I'm going to share with you today is our journey to, now I guess we have between 200 and 500 cavities. We're still nailing the number down, each with a cooperativity of 10. And at least 200 of them are degenerate to within 1 line width. Okay. So let's just hop into how we do this in practice. Yeah, great. So, I think it's fair to say we're not the first people to think about putting atom arrays in cavities. I would say our group has steered clear of that because we have very little experience, at least until Adam arrived, with atom arrays. So there are all kinds of really beautiful experiments there. But I have to say, at some level, the thing that inspired me the most on this is my decades-long love-hate relationship with Dave Schuster. Because he's constantly making comments like, I can make arrays of cavities, I just nanofabricate them. Why is that so hard for you guys? And so we've been struggling to find a way to leverage optical cavities to do things in parallel and do things better than circuits. He's trying to put himself out of business. So this is a collaboration with his group. So let's hop in. Cavities give us a factor of finesse enhancement in light collection efficiency compared to a lens that subtends the same solid angle. I think of this expression as saying, this is the solid angle subtended by my cavity mode. The cooperativity is just that solid angle times the finesse. So you should think of the cavity as just enhancing the collection solid angle. So the bad news is that for a typical optical cavity, this collection solid angle is more or less lambda over the radius of curvature of the mirror. You can do a little bit better by moving towards concentric, but fundamentally, most optical cavities kind of look like this. This drawing is to scale. Let's watch this mode as I vary the length of the cavity. The nice little pencil mode here. And so now we're a little past confocal. And as we hit concentric, we'll see the mode size start to drop. But even at like half a micron, or excuse me, at 50 microns from concentric, the NA is quite low. And so our objective is to get to quite a bit higher NA. So if you're at this low NA, of course, what you have to do is have a pretty high finesse. My group's experience, at least, has been that working at high finesses is a recipe for things getting on your optics and misery. I guess there are people who are, probably most of you actually are way better at that than I am. But our solution was to make a reasonable cooperativity cavity at the lowest finesse we possibly could. So my favorite talk title is A Race to the Bottom, and I use this often. So this is a cavity with a cooperativity of several and a finesse of like 20. And the basic key idea here is that if you can go to very high NA for your cavity mode, then you can tolerate low finesses. And the finesse, the scaling with the waist is so strong compared to the scaling with the finesse that you can think about putting optics in your cavity. Okay, so this is the fundamental sort of breakthrough for the cavity geometry. This came from initially a discussion with Mark Kazovich, and then Dave Schuster and I chatting with Matt Jaffe. We are used to the waist size of a cavity being more or less the geometric mean of the radius of curvature and the wavelength. If you put a lens in the cavity, you have a term that scales like the focal length of the lens and the wavelength, geometric mean. But by making this arm longer and longer, basically you completely break that scaling. So you can make this as long as you want, and you can get as small a waist as you want up to the aberrations of your optics. And so we did this. If you came to the lab and saw what was in vacuum, this is a C140 fiber coupling lens inside of the cavity that gives us this large cooperativity. And so, we've seen strong coupling of individual atoms. We've been able to perform high fidelity state detection. But what I promised you was an array of cavities. And this is one cavity, right? We'd like one cavity per atom. So how do we get each atom into its own cavity? Well, what we say is we already gave up really high finesses by putting a lens into the cavity. So let's just put more lenses into the cavity. So this is the geometry that you should kind of imagine. We have a 4F imaging system over here and a 4F imaging system over there, and a micro lens array here. So let's ignore this micro lens array for a moment and just think about light coming from one of these atoms. It gets re-imaged onto this mirror because of this imaging system, and then re-imaged back onto the atom. For any location over here. And so what that means is that basically, from the perspective of the atoms, they are sitting on top of a mirror. You may as well ignore everything to the left of this line. The atom is sitting at the antinode of a field on a planar mirror surface. Here we have a demagnifying telescope. So from the perspective of this cavity, well, I have maybe atoms spaced by 5 microns here, but for understanding the cavity, I may as well actually ignore all of that. And imagine I have a planar mirror over here, right? So now I have a planar mirror and another planar mirror, and that should just give me an array of cavities that are fully degenerate if I put those two mirrors close enough together. So this comes back to Brandon's comment. Why do I need this lens array? Well, if you don't have the lens array, any small aberrations lead the beam to walk off over many round trips. The lens array stabilizes you. As Ben has pointed out, if your atoms are strongly enough coupled, they could stabilize you, but we didn't want to bet on that. And so what we do is we put an array of little lenses here, and you should just imagine this like my earlier slide. It's an array of lenses between two planar mirrors, and that makes an array of little cavities. And now you can imagine that we're just demagnifying those cavities down onto our atoms. And so this is our recipe. You can calculate it that way. It all basically works out just like that. So this is what the cavity modes look like. And this is a little numerical ray tracing simulation about what happens to rays that start at different locations in the atom plane and go around many round trips through this system without a microlens array. And what you find is that even the slight spherical aberration of your lenses makes them get lost in many less than 100 round trips. And then you add the microlens array and you build a little island of stability that kind of traps rays even in the presence of slight aberrations that try to redirect them, so centered on each of these points. And you might say, but cavity modes are wave objects. Why are we talking about rays? And again, I want to bring us back to this point that we should think about all of these systems in terms of rays that come back to themselves and then doing a paraxial expansion around those rays. Okay, so this was the system that we had in vacuum for those earlier experiments. In fact, the end mirror of the cavity is outside of the vacuum chamber. This lens is about 1 millimeter from the atoms. So 1 millimeter is not great, as I've pointed out. It's not terrible, but it's not great in terms of stray fields. But again, this is also not a cavity array. How do we turn this object into an array? Well, it turns out this is basically half of the other object that I drew for you. And so what we did was just add a second lens to make a 4F imaging system, added a planar mirror, and add a microlens array here. And so we can characterize these cavities. Each one has a cooperativity of 1 to 2 in practice once we make this into an array, at a waist size of around 1 micron and a finesse of around 10 to 12. And we were then able to image single atoms through this thing on timescales of a couple of milliseconds, mostly limited by technical things. We project that this current system could get down to a couple hundred microseconds. But the good news is we were very worried about cross-coupling between the cavities and the optics. That is not a problem at all. This just really works exactly as you expect it to. Eventually, what you would like to do is use this for a networking demo or a networking device. And so what we did to just prove out those ideas is couple a few of these cavities into fibers in a little fiber array package and just show that we could detect the atoms through these fibers. Broadly, I would say this kind of an approach points to all kinds of really fun opportunities beyond quantum computing. If you like putting nonlinear optics in your cavities, we've now started to do that. The finesses are low enough that we can put piplin crystals in the cavities to do frequency conversion in a cavity. The The one we did it in didn't have an atom, but you could imagine doing it in the cavity that has the atom so that this atom directly speaks 1550. You probe your cavity at 1550. You get reflections and transmission at 1550, but the atom speaks 780. So we have some fun results playing in that space. We're also working closely with Amir to couple these cavity arrays with very high sort of resonantly enhanced fiber coupling to arrays of nanophotonic devices. The last thing I want to say is that we have a big upgrade that's ongoing in the lab. Those of you who got lab tours probably got to see a little of this. From our previous demo, our maximum finesse was 30 to 40. We had 40 cavities, and they were about 1 millimeter from the A-sphere. The whole cavity itself is about $2,000 in parts. It's really amazing. The human effort was a little more, but so this is what the mode structure looked like, and this is the mode structure of the new cavity. And so this is data hot off the press. I've been informed that this is not very good data. It looks pretty good to me. This is an array of 500 cavities. This central 250 of them are degenerate to align with at a mean finesse of over 120. So that's a cooperativity per cavity of like 11 over hundreds of cavities. And our new aspheric optics move us 8 millimeters away from the optical surfaces. So, our experience with Rydberg's has said this will be more than enough to really just address in situ. The complaint about this data is that there's a little bit of residual astigmatism. Anna, Daniel, and Adam have been working very hard on understanding the alignment degrees of freedom in this system. There's really beautiful moire physics if you like moire physics, and there's also really beautiful moire physics if you don't like moire physics. And so anyway, this alignment I think can get even better than what we see here. Okay, so I have 40 minutes total, and I'm 20 minutes in, correct? Good. Okay. But what I wanted to say is that this idea that you should be thinking seriously about micro lenses and micro mirror arrays all over the place, I think the opportunities are quite broad. We've now put a micro lens array in front of an EMCCD and imaged during our readout of the EMCCD. And then what you can see is that different pixels, you can tilt this micro lens array such that each row of the EMCCD is only exposed to 1 pixel in your image. And so as you do your readout at, say, 5 megahertz, you get 5 million frames per second from an EMCCD. And so this is just looking at an AOM as the beam moves around in space. But you can now start to imagine using this for high latency, admittedly, but very high speed readout of atom arrays. But then we also wondered, is there a way we could make really high speed spatial light modulators using micro lens arrays? And you're like, well, a micro lens array is a passive device, John. What are you talking about using it as a modulator? Let's start with an information theoretic question. If I want to have 100 by 100 spatial light modulator for controlling a quantum repeater, and I want to be able to make decisions at 1 million frames per second for fast feedback, that's in the neighborhood of 10 gigabits per second of data that has to go through that device, right? So what devices do AMO people work with that have 10 gigabit data rates? Well, turns out spatial light modulators have those data rates almost, but we can't use them fast. The other object we have is an electro-optic modulator, right? And so what I would like to tell you a little bit about now is a way to make a spatial light modulator that can run at, for us right now, it's going to be 10 by 10, but at 10 million frames per second. And the way it works is by developing a new type of 2D spectrometer. And as you'll see, it has a lot in common with a cavity. So how should you think about this object? Well, we're going to have a 2D spectrometer that you send in light of some frequency or some set of frequencies. And what it'll do is take light that comes in at some frequency omega 0 and put it here. Omega 0 plus delta omega goes here, plus 2 delta omega, so forth, up to n delta omega. And then n plus 1 delta omega appears here. N plus 2, 3, 4, 5, 6, 7, 8, 9, 10. So in other words, if I have 100 points, I need to have a spectrometer that gives me my x coordinate being like the frequency mod this distance. And my y coordinate will be the frequency kind of flow divided by that distance. So then the question is, how do I use this? Well, a fiber electro-optic modulator can generate a comb of frequencies, right? And so by driving this with a crazy arbitrary waveform generator, I can feed in a comb that makes whatever image I want. So if I just have a single tone and I sweep its frequency, I would expect to generate a movie that looks like this as the frequency sweeps. If I have a comb that looks like this, right, then I could make a face. So that's great. We've got everything we need except that spectrometer. So when we started on this journey, we knew about 2 types of spectrometers. The first, maybe you've heard of, is called a diffraction grating. And diffraction gratings are really nice because every frequency gets mapped to an angle, which was kind of what we thought we wanted, right? The problem is that if we want to use a 100 or 10 gigahertz EOM and make 10,000 points, like a 100 by 100 array, we need 1 megahertz of resolution. So how big a grating do we need for 1 megahertz of resolution? About 300 meters. So that's too big. We talked to the folks who run the football stadium. They weren't comfortable with that. But the way to think about this is that your resolution here is coming from the phase difference from this propagation length of order lambda, okay? The way to get more resolution is to put 2 mirrors and have a lot of distance between them, right? There, it's very easy to get, it's very easy to get megahertz scale resolution. The problem is only 1 frequency goes through and all the rest of them get reflected, right? So you could imagine reflecting sequentially off of 10,000 cavities. There are some bad things about that. But what we would like to develop is something that looks like a cavity, but gives us an angular spread in output. So as Zev pointed out, it turns out this object exists. It's called a virtual image plane array. I'd like to talk you briefly through how this thing works. And I think once I do that, it will be immediately clear what our solution is going to be. So how does this thing work? Well, I send a beam in here, and it bounces around a bunch of times. Each time, a little bit of the power comes out. And now what you should imagine is that there's a relative phase between these beams set by this path length and the wavelength of the light, or equivalently set by the frequency of the light and this like free spectral range like distance. And so if I add a lens here to interfere all of these different beams at some point, well, if I just had one of those beams, I get this wide Gaussian. But with n of them, I get this much narrower Gaussian. It's n times narrower, right? And as I vary the relative phase between the beams, the location of that Gaussian changes, okay? And so the picture you should have in your mind is that the number of resolvable spots I'm going to get from this is just set by the number of passes that I have here. And the spectral resolution is set by C over 2L over the number of passes. So this, it's sort of amazing. The calculation is literally identical to a Fabry-Perot cavity. We've just unwrapped it in space, okay? Yeah?
Is that just the Fabry-Perot of our grandfathers?
Yes. At some level, yes, it is a Fabry-Perot etalon. Okay, so if you want to be concrete, there is a difference, which is you have to get the light in somewhere. So I am not sending a beam in and having it interfere with itself repeatedly like you do in a Fabry-Perot. I'm kind of sending the beam in around the coating, right? And then having it bounce around a bunch of times. But spiritually, it has a tremendous amount in common with that. Okay, so what is the challenge with this thing, and why is it called a virtual image plane array? Well, because we deal with Gaussian beams here. So that beam is diverging. And to see how the next round trip diverges, you should imagine that this next one came from a spot that was slightly further back, and the next one from a spot that was slightly further back. So that's not good, right? That means I need to make this beam quite big, or this thing very thin. If I make this thing thin, then I don't get much spectral resolution, right? Or I can make it thick and not get very many passes. So the question is, how do I deal with the fact that this beam is diverging? The answer, of course, is a microlens array, right? So this is not how we actually do it, but I think, spiritually, this is the easiest thing to understand, and it's what we're moving towards. You make a micromirror array here, and you just bounce off of it repeatedly. And basically, the stability diagram for this thing is just like the stability diagram for a cavity. We've played very fun games where if you slightly displace this input beam, you can see harmonic motion of the output beams relative to where they should be, right? That GUI phase of this object is really just how many round trips it takes the thing to come back to where it started. So this all does exactly what it should do. And so this allows us to make this quite a bit longer, up to a couple of centimeters, and get tens of round trips, no problem, with off-the-shelf components. If you want to make it even longer, does anyone want to guess what you should do? You should add a 4F imaging system, of course, right? And so this is just a 4F relay. Light goes here, goes there, comes right back. We're just getting ourselves more spectral resolution at the output. And so now going back to what we wanted at the front end, we need this 2D spectrometer. What is it? It is a short one of these real image plane arrays. And that gives us low frequency sensitivity so that for large frequency changes, we move in the Y direction. And then we have a longer one cascaded after it that moves our frequency rapidly in the X direction. Okay, in practice, that object looks like, well, in practice, you probably saw in the lab, in practice, it doesn't look like this. In practice right now, it's horrible. But it does work very beautifully. The first one's always horrible. The magic is that it works. And so this is the short one in a running wave configuration rather than that standing-ish wave. And then here's the long one, again, in a running wave kind of a configuration. And we now have a working 10 by 10 demo from a cell phone from last week. So this thing can run at 10 million frames per second. The cell phone can't image at 10 million frames per second. So you're seeing something a little bit slower. When I mentioned this to Jeff Thompson, he wanted to know how much crosstalk we have. It's a few parts per thousand right now, limited by the fact that the thickness of our lenses are slightly different at the few nanometer level. And so what we've had to do is correct those phase errors with one static hologram outside of the RIPA. But that works great, no problem. So next up is going to be a 100 by 100 demo at 1 megaframe per second. Using one of Marco Lonchar's 100 gigahertz EOMs, we think we can get to 1,000 by 1,000 at 100,000 frames per second. If you really want 1,000,000 frames per second at 1,000 by 1,000, well, then you need 10 of those EOMs, each driven with a slightly different wavelength. And we think that's also possible. And that will only need a terabit of data per second to drive it, which we think we can get with about 30 RF socks. But I do think this, but to be fair, you're like, that sounds crazy. But like, if you want to have arbitrary movement of atoms in a quantum computer, like, this is what it takes, right? That data bandwidth is just what you have to do unless you want to leverage huge amounts of transversality. And it's looking more and more like the thresholds and rates for these LDPC codes are just better. So anyway, pick your poison. I can't help, I want to show one more fun thing here. I have a couple, 3 minutes, okay. So I was talking about this EOM, like it only makes one comb of frequencies, right? But of course, it makes a blue order and a red order, and then a whole bunch of intermodulation products if we're using it at any kind of reasonable efficiency. So how do we only isolate the blue family of tones? Well, we've developed a new type of cavity that has a flat top transmission spectrum instead of a Lorentzian spectrum, okay? And it comes from basically cascading two cavities of the same frequency with coupling between them. And that doesn't just give you Lorentzian squared, because there's actually back action from the second cavity onto the first cavity. They hybridize, and that gives you a transmission spectrum, which is like a fourth order Butterworth filter. Okay, and so how do we implement this in practice? Well, nobody wants to lock two cavities in sequence. We've done it, it's miserable. What you can do instead is use two polarization modes of the same cavity as your two modes, and then you need to couple them, and you couple them by putting a glass plate in and squeezing it right up until before it breaks. And we know where that point is. We know it very well. But it's quite amazing. When you do this, you get a cavity with a really clean 1/delta to the fourth suppression outside of the resonance, and within the resonance, you get this beautiful flat top. And then you send light in a superposition of the two polarizations and look at the reflection in the opposite superposition, and it just goes. So anyway, I think that's probably a good place to leave it, except to say that this work is the result of many years of hard work from a number of people. This is just a small subset of the people who've pushed on this science. The small waist cavities have been pushed on by this team. This VIPA was pushed on actually by the hybrid millimeter wave team. But I want to say more generally, the ideas were actually even developed largely by understanding aberrations in these twisted cavities. So it's been a fun long-term effort. So thank you, guys.
Very nice. I just curious about the fundamental limit of this
The waist diameter. So how small could we make it? So the answer is our lenses have an NA of about 0.58. And we tend to operate at an NA of like 0.3. Why do we do that? Because if you go up much more than that, even at quadratic order, you start to clip, right? And you need to go around a bunch of times, so you can't tolerate much clipping. The other thing that I would say in practice is that at some level, cavities can tolerate more aberration than normal imaging systems, because our point spread function doesn't get much bigger as the aberrations come in. In reality, they can sort of actually tolerate less, because what that aberration does is mix in higher order modes and limit your finesse. And so I guess my take has been, we're operating at like 1.2 lambda, 1.3 lambda. I think going much below that is going to require optics that are good to a few nanometers. So far, we've been able to get optics that are good to about 10 nanometers. But my sense is, in general, you always do better to have the largest waist that you can possibly tolerate and spend the rest of your NA not suffering in finesse, right? I mean, there's always this thing like the best cavities are super low NA and very high finesse. So I think our take is that we won't go below a micron because there's just not an argument to do it. Does that make sense for where we're pushing?
Yes. One question I would have is, Ben this morning showed us how multiple cavities can also get you down to small weights like such a micrometer. So, in which case is it better to use your parallelized version, and in which case would it be better to use this multiple cavity, which in principle also has.
So here's what I would say. For the science that Ben is doing, his is way better because his modes don't need to actually be degenerate to within a line width, right? Because he's working at a large detuning from the modes. And so what I would say is if he could actually get his modes degenerate to within a line width, his approach would be way better, but that requires that your optics be perfect to lambda over the finesse, right? Which is a high bar. Ben is not just detuned from the P state, he's also detuned from the cavity. For his science, that doesn't affect the quantity that the cooperativity light quantity that he works with. If you want to collect photons from your atoms, if the modes aren't degenerate, that quantity just drops off. Does that make sense?
Is it, but is it the cavity line width or the atomic line width which matters?
I think if you compute the below saturation scattering rates, I think it's the cavity line width, but we should validate that. I agree.
I think it would depend upon the regime a little bit. Like maybe if your G is a lot higher, then you get better. And if the mode gets small enough with the multi-mode, I think maybe it does like work out.
I think it's a great question because if you can be totally agnostic to where exactly your atom sits and just make a degenerate cavity, that's super nice. I agree.
Did I hear you correctly say something about resonantly enhanced fiber coupling?
Yes.
What does that mean?
That is basically a statement that